Hello everybody. So first of all, I would like to thank all the members for Cheers for being here today and to accept it to evaluate this paper entitled Open Phytotron, a new IoT device for home gardening. So this presentation will be presented by me, Rashida Et Abdelwahid. I'm associate professor at the University of Hassan II Casablanca and a doctor in computer science. So for this, we will follow this following planning. First of all, we'll give a small introduction about home gardening. Then we'll present related works and the works that we have studied during our research. Then we will present our phytotron interoperability architectures and the material that we have used to implement our then we will present a demonstration and the so we'll go to the introduction. So Phytotron is a grow room that creates artificial growing conditions to accelerate the natural growth of plants. So the goal behind the creation of this solution or for Phytotron is to design a versatile device that can be used on different type of equipment and can be interfaced with existing systems such as Home Assistant, Open Hub, Node-RED, etc. So Home Assistant or Open Hub are platforms of that offer more interoperability in our systems. So during our research, we have studied different works and solutions related to our Phytotron. So, for example, we can have Sunny and all that they have such as a web monitoring platform using wireless sensors and an actuator network of aeroponic grow chamber in which temperature, light intensity, and pH level are transmitted via internet to a server via GSM and displayed on a website. So, however, in case of network unavailability, the system cannot work. And we have studied also different work. For a limit of time, we cannot present all this. So we have note different limitation of these solutions. So lack of architectures that offer more flexible interoperability and integration with existing IoT platforms. So in the case also we have concluded that in case of network unavailability, the system cannot work for some solutions, and some solutions of Phytotron are difficult and complex to deploy. For this, we have proposed our interoperability architectures for Phytotron. So growth chamber generate a large amount of heterogeneous data, numerical or not, of type continuous, discrete, multidimensional or not, which must be collected and treated. So Wi-Fi is widely available inside the agriculture chamber. It's easy to connect microcontrollers equipped of sensors on the Wi-Fi network. In order to obtain autonomous unit, take a local decision, we have implemented a home assistant in each room, which collect and process data produced by a set of USB32, which is a microcontroller equipped of sensors managed by USB Home and an add-on for Home Assistant. So each microcontroller USB32 is connected on Wi-Fi and support over the programming OTA. So the Home Assistant installed on a Raspberry Pi process data and afterward send them to a central point in the home garden by means of MQTT protocol. So this is a generality of our proposed architectures. So in this figure, we have described each layer of our proposal architecture, which based on 7 layers. So the infrastructure layer represents different connected things which acquire environmental information or achieve an action on this environment. So we have in this layer sensors and actuators that we have used in our Phytotron. Middleware layer ensure collect data in the cloud, data processing, data cleaning, integrity, verification, normalization, data sorting and transformation, data interpretation with machine learning algorithm, and finally storage in big data. So in this line we have present we can make or use microcontrollers. For our case, we can use Raspberry Pi for to control and to treat the different function. Service layer provides critical and reliable service for various open data university package, and application layer uh, propose different manner of data presentation, visualization, and consultation to end users. So we have also the the service layer. Okay. And the application layer, it's used to just to visualize the data that we have taken from the actuators and the sensors. And we can also develop our own mobile application to visualize data. So this is our physical architecture that we have specific to our case of Phytotron. So we have used in the layer of infrastructure, we have used some materials, some uh, so sensors, sorry, sub sensors for temperature and soil. So information layer, we have used a Raspberry Pi to collect the data from different actuator for different actuators and sensors, and we can this Raspberry Pi is used also to install different platform of connectivity that I have present Open Hub or Home Assistant. So in the layer of communication layer, we have used MQTT protocol by installing Mosquito broker like a broker and server Mosquito like a broker of our protocol MQTT. The connectivity layer, we have installed Home Assistant in our Raspberry Pi, and for the middleware, we can use cloud to storage the data and big data to treat our information that we have used. If we have a big a big data in server layer, we can create or develop some functions for related to smart farming. And the application layer, we have used Node-RED to visualize data that we have taken from our sensors and actuators. So the material is made up of 4 packages. The first package contains the application hosted, the microcomputer, which manage the network of sensors. The second package incorporates microcontrollers used to sense the environment and to operate the actuators. The third collect different sensors used in this application. Finally, the fourth package include actuators. Uh, so this is our environment sensor node. So we have used different materials to implement our prototype. So microcomputer is our OSP32 is used to have software need to manage and monitor the network of sensors. The Raspberry Pi is used to host Home Assistant, which can take local decision and turn off on or off actuators. It's also played the role of local gateway and transfer data to central point of building with MQTT protocol. So the microcontroller are used to connect sensors and transmit the data. In our case, we have used OSP32 for or like a microcontroller. And we have used different sensors like IM2301, which is a sensor to measure the temperature of the air, and we have used soil humidity. This sensor can measure the humidity of soil, and LCD to visualize the different numbers taken from IM and soil humidity, and prepare to connect these different materials. So we can also use this sensor to use to measure the soil humidity, but uh, this sensor is unique because it contains a model of Bluetooth. Okay, and we can use some actuators like peristaltic pump to pump the fluid, a real-time clock, push button to make to to push to put on the light or put off the light, and we have used LED strip, which is LED artificial LEDs, and we have used for power supply 12 volt. So this is our implementations like this, our Phytotron in code chamber, and we have used several sensors, actuators, and to implement our proposition. So Home Assistant, this is a presentation of the Home Assistant or the platform of connectivities. So some smart home automation systems such as Home Assistant or Open Hub have been developed to interconnect a large number of sensors using different network protocol. So Home Assistant is an open source automation solution hosted on a simple Raspberry Pi or similar computer. So it allows to study the state and control many devices from a simple and user-friendly interface that respects privacy and does not publish any information to the cloud. So this platform can be diverted to be implemented in every auditorium, office, laboratory, university room, etc. So this platform can publish and subscribe to MQTT topic to exchange between them and transfer data to central point located in our building or home assistant. So the interoperable architecture that we have used, so we have implemented our prototype, and we have connected our prototype to born Wi-Fi to send data to the Mosquito broker or server of MQTT, and then this server we can visualize the data showing in our Mosquito or server of MQTT by using Open Hub or Home Assistant or Node-RED. So this is the process that describes the functionment of our of MQTT protocol. So first of all, for example, you can have a client MQTT like Node-RED, or just
Miss Rashida, okay, you have the problem in the sound. Okay, I can't hear you.
Okay, can somebody confirm that they see my screen?
Yes, you can start.
Yes.
Okay, and then I will play the video of the presentation. Please just verify that my audio is working. Good day, everyone, and welcome to this presentation on an IoT. Okay, can everybody hear the audio?
Yes, perfect.
Thank you. The data logging instrument for monitoring and early efficiency loss detection at a photovoltaic generation plant. I would like to advise anyone that is interested in more of the technical aspect of the study to go read through the article, for this will just be an overview of the research. Here we will have a quick look at the structure of the presentation. We will start by going through the introduction of the study, and then we will look at what the purpose was setting up the study. Next, we will go through an overview of soiling and the operations of the device, which will be describing in a bit more detail the workflow of the device. We will then have a look at the results, where we will be showing some of the technical specifications of the sensors being used. And finally, we will go through the conclusion and recommendations. Renewable energy sources is gaining popularity across the world. Renewable energy is the way forward for power generation, since fossil fuels are not indefinite and is being depleted rapidly. One of the major players in the renewable energy industry is photovoltaic generation, since it is easy to set up commercially and also used in large industrial solar farms. The benefits of photovoltaic generation is numerous and well documented, and includes topics like renewable energy sources, reduction of electricity bills, diverse applications, low maintenance cost, and many more. One of the major downsides of photovoltaic generation is the fact that the conversion from solar radiation to electrical energy is quite low in most commercial applications. The conversion rate of the solar radiation converted into electrical energy is approximately 15 to 20%. Technological advancement in the field of solar energy production has increased this percentage somewhat, but it is unaffordable for most commercial applications. This is where this research comes in, where instead of increasing the productivity of solar panels, we reduce the loss of efficiency of solar panels and thereby increase the overall productivity of the solar installation. The purpose of this research was to describe a device that could be used for the early detection of loss of efficiency of a solar installation, so that immediate action can be taken to rectify the fault or problem and therefore reduce the losses in the system and increase the overall efficiency of the installation. Some of the goals were set out starting the research includes using affordable and accessible materials for consumers, but not limiting the system to cheap, inaccurate, or unreliable sensors and components. Another goal was to design the system in such a manner that it will be easily adaptable to real-world applications for commercial and industrial uses, in either home installations or large-scale solar farms. And lastly, the device needed to be scalable, so that the same device could be used in commercial applications as well as industrial applications. As I mentioned above, photovoltaic generation has inherent problems, one of which is soiling. Soiling in the case of solar panels is exactly as bad as it sounds. This is the process whereby sediment, including sand or dust, pollen and plant matter, covers the surfaces of solar panels, reducing the solar radiation that reaches the solar panel and in turn reduces the efficiency of said solar panel. Soiling is a major problem in warm and dry regions where solar radiation is normally higher and solar panels are more commonplace. As described by the Köppen Climate Classification Scheme, these regions fall under Group B and include arid and semi-arid regions. In most commercial applications, solar panels are not visible on a day-to-day basis, and in most industrial applications, solar panels are not inspected on a daily basis. The process could be, the proposed device could detect problems like this as soon as they occur and then can be solved immediately to reduce a loss of efficiency. Here we can see a figure describing the effect of soiling. The main focus of this figure is evenly distributed dust concentration on the surface of a solar panel. It is evident that the soiling has a major negative effect on the efficiency of the solar panel, and by simply knowing when the solar panel needs cleaning, the loss of efficiency can be prevented without excessive cost. Before we get into an overview of the operations of the device, I would just like to mention that all the technical considerations that was made for the selection of sensors and processing units, as well as the data collection and storage devices, is available in the article and will not be referenced here. Temperature sensor is connected to the solar panel, where the temperature of the solar panel can be measured most accurately. The voltage and current sensors is then connected to the output of the solar panel before feeding into whichever device is used to manage the power from the solar panel. The data collected by the sensors are then fed into an Arduino Uno, or the processing unit, and is then encoded to an appropriate form to be sent through the Sigfox transceiver module. The reason for encoding the data is there's a restriction on the amount of bits that can be sent by the Sigfox transceiver. The Sigfox transceiver does not require cell phone reception or internet connection to operate. Instead, it uses its own network. Therefore, installations in remote areas will not be hindered by the lack of infrastructure. After the Sigfox transceiver has transmitted the data, it is then received by the backend of the program, which is the cloud of the Sigfox servers. The backend doubles as the cloud storage for safekeeping of the data and to access historical data. The data is available through an API, where the front end collects the data and decodes it into a format that would be easily understandable by the end user. The data collected from the device could easily detect any loss of efficiency and could even suggest some possible solutions. The prototype was installed into a test system where the expected maximum voltage of the output solar panel would not exceed 65 volts. The allowed minimum input voltage of the Arduino Uno is 5 volt, and the maximum output voltage from the sensor was 4.94 volt. The quantization error percentage of the voltage sensors was calculated to be 0.192%, and the solar panel's maximum voltage output of 65 volt, the power consumption of the voltage sensor, was calculated to be 14 milliwatts. More of the technical information is available in the paper, including a graph of power consumption versus voltage input. The temperature sensor used had the upper and lower limit of 125 degrees Celsius and negative 55 degrees Celsius, where the expected operating range of the solar panel in the test system was from negative 10 degrees Celsius up to 100 degrees Celsius. Within this range, the temperature sensor had a tolerance of 0.5 degrees Celsius, which is acceptable. The expected current output from the test system was 7 amps, and the maximum current measuring capability of the current sensor is 50 amps. At 50 amps, the expected error of the current sensor was 24%. The operating temperature of the current sensor is from negative 40 degrees to 150 degrees Celsius, which is again within the expected temperature range. The rate at which the data was sampled is 0.01 Hz, and the calculated Nyquist rate was 0.005, which is acceptable as well. The reason why the sample rate is so low is because deposition does not happen overnight, and dust storms have a surprisingly low effect on the deposition rate. In conclusion, all the goals that we set out to achieve was met, where we could detect the loss of efficiency early on and solve the problem to reduce the time that the solar panel was operating at low efficiency. The sensors and processing devices used was selected with cost in mind and was well within affordable classification even by commercial application standards. The device came out to be modular, and multiple devices could be connected for the same backend, and the data could be stored per device on the cloud. The increase in efficiency will depend on the severity of each issue, as well as how fast the issue can be resolved. Recommendations would include using the most appropriate sensors for specific applications and using the most expensive or accurate sensors that could be afforded. I want to thank you all for your time, and if there is any long form questions, feel free to email me or Dr. Lewis at the following email addresses. Okay, thank you everybody. If there's any questions, feel free to type them in chat or again email them at the above mentioned email addresses.
I think Kautar Hafidi is not here. We can pass to Bouawad.
Okay, I will do the presentation. If there is a problem, I will just record the video presentation. So I will establish with the presentation, and then if there are some issues, I will switch to the video presentation.
It's okay. You can start. Thank you.
Okay. Can you please confirm me the share of the screen if it's okay?
Yes, it's okay. You can start. Thank you.
Okay, thank you. Good morning all. First of all, I want to thank all of you for being here. I am Alauddin Bouawad, PhD student at CWeb team at IMI Rabat. Today, I'm very pleased to present our work titled The Key Layers of IoT Architecture. As we know, actually, the Internet of Things has emerged our world and has become preponderant. In this objective, several architectures were proposed in the literature. Our work focuses exactly on determining and selecting the key layers that constitute the different architectures. For this purpose, this presentation follows the plan as described. Firstly, an introduction about the relationship between IoT and cloud computing will be highlighted. In second, we will present the related work that has been prepared in order to determine the IoT architectures in cloud environments, which constitute the main subject studied. Thirdly, we will present the analysis conducted of IoT architectures. And fourthly, we will present the results and discussion of this research. And finally, we will end up the presentation by general conclusion and future works. Today, many objects have become accessible to the end users, such as sensors, smartphones, tablets, smart TVs, and smartwatches. Until now, these connected objects remain limited in terms of computing and processing capacities as well as storage capabilities. The cloud computing thus becomes complementary in order to compensate for the shortcomings of connected objects through storage, processing, and computing platforms. The architectures of IoT systems in cloud environment are multiple and heterogeneous. The diversity of IoT architectures in cloud is mainly manifested in the layers, each of which responds to specific need. A specific architecture does not describe the layers exhaustively in order to guarantee the support of all functionalities, allowing it to be deployed in any environment. Each architecture naturally has limitations in terms of functionality and organization related to the layering process. The purpose of this research is mainly to analyze the architectures of an IoT system in cloud environment proposed by the literature. This in order to identify their layers and use those that are common and then those that are relevant. The research question that guided our literature review is what are the architectures of an IoT system in cloud environment? In order to identify the articles that will allow us to answer this question, the research method followed is divided into 6 steps. Number 1 is the choice of scientific databases. Number 2 is the definition of keywords to filter the articles to be studied. Number 3 is the use of relevance ranking tools provided by databases. Number 4, prioritization of articles published since 2009. Number 5, prioritization of articles published in peer-reviewed scientific journals. And finally, reading the title and abstract to identify the articles that actually deal with the subject. The result of our method is 21 articles selected and 32 architectures that were selected to be the subject of our study. We note notably the architectures that aim to bring the cloud layer closer to the edge part, like fog computing, cloud edge beneath, central office re-architected as data center. We can also note the architecture that deal with the virtualization technologies, like software-defined machine, network function virtualization, and software-defined network Internet of Things. We have also the architectures relating to the standardization organization like IoT architecture, industrial internet reference architecture. In addition, we can notice the architecture that are specific to domain, like home cloud, firm to cloud, home health hub internet, and sensor data as a service. And finally, the architectures relating to the publisher and suppliers of the market, like SAP architecture, Microsoft, Intel, and Borgia architectures. The detail of the research is referred to our article, Architectures and Emerging Trends in Internet of Things and Cloud Computing, Literature Review. This article is in state of impress and will be presented in December at the 4th International Conference on Advanced Systems and Emerging Technologies. Following the selection of these 32 architectures in cloud environment, we have identified for each of them the layers that support them. First of all, classification of the layers by means of syntactic analysis is carried out in order to group similar layers together and eliminate the duplicate one. Second, a semantic analysis is performed on the layers in order to understand their functionalities and their level of intervention. This allows us to group these layers by level when their objectives and functionalities are the same. We were able to identify 12 layers. The first layer is the physical, relating to the connected objects. Layer number 2 is the layer relating to the virtualization of connected objects. Layer number 3 is the virtualization infrastructure layer, which corresponds to the different technologies used to instantiate virtual objects. Fourth layer is the layer relating to interconnection and exchange data between the different objects. The fifth layer is the access, which is relative to the different gateways and aggregators that centralize the connected objects. And the layer number 6 is the network layer, which ensures communication between connected objects and the cloud part. The seventh layer is the middleware layer. The eighth layer is the business layer, which is responsible for presenting business application to end user. The ninth layer is the cloud, which is also very common between all the architectures. The 10th layer is the application, which provide the user with the services and applications necessary to meet his needs. The 11th layer is the application relating to virtualization. And finally, the 12th layer relates to applications specifically dedicated to the user for needs in terms of access management and security issues. By analyzing the percentage of layers included in the selected papers, notably the 32 architectures, we can see that of the 12 layers surveyed, the highest percentages of coverage are mainly 84% for physical layer, 63% for cloud layer, 41% for application layer, 38 for network layer, and 34 for access layer, and finally 28 for middleware layer. We can note that the layer 1 corresponds to the more popular. It is evident because the Internet of Things are based on the connected objects which constitute the physical layer. For the others, layers which have the lower percentage of coverage, like layer number 2 or number 3, specific to virtualization, these latter are not preponderant because they are specifically dedicated to virtualization technologies, which is the most architectures doesn't deal with it. The key layers correspond to the physical layer of connected objects, the access layer, the network layer, the middleware layer, the cloud layer, and finally, the application layer. The number of layers proposed in an architecture is very important factor, as it is the determinant of the coverage of architectures in terms of functionalities and interoperabilities. The following slide shows for each architecture studied the distribution of the number of layers. We can note that the number of layers proposed per article is between 1 and 6, depending on the nature of the architecture. This leads us to believe that the proposal of target architecture must cover at least these layers and be able to provide layers in terms of functionalities and in sufficient number to adapt to any concept. In conclusion, we have studied 32 architectures and we have been able to identify a total of 12 layers that support them. After the analysis of these layers, we found 6 that are common and proposed in the majority of these architectures, notably the physical layer, the access layer, the network layer, the middleware layer, the cloud, and the application layer. In perspective, the key layers identified in this paper will constitute the basic core for the proposal of a reference target architecture. The layers that will be proposed in the future work will be detailed and decomposed into sublayers in order to be able to find out all the functionalities of each sublayer. If we take, for example, the cloud layer as an example, we can make an initial reflection about the sublayers like containment, storage, processing, data visualization, and others. The following presentation has ended. Finally, I want to thank all of you for your attention and for your presence.
Okay, thank you very much for your presentation. Okay.
Okay. If there is
thank you very voilà. Any questions, please? If there is any question. Any questions, please? No? So okay.
One question. Yeah.
Okay.
So I would like to thank the presentation for the presenter for his presentation. It was very clear. So my question is, so this 6 layers that you have described in your presentation, so it's we can say that it's a general each general architectures must have the 6 layers, or just we can say that each specific realization or project of IoT can has his own physical architectures. So we cannot we cannot say that everyone that has made a project of IoT must have a layer of virtualization. So it's depends of the use of this project. Can you answer me?
Okay.
Yes. First of all, I want to thank you for your question because it is very pertinent. The idea of the analyzing and the sorting on conclusion by the 6 layers of IoT, it is generic. It means that our next and future work will consist mainly on defining all the layers that can be included in an architecture, and after that you can use the layers that correspond to your context and your own domain or your environment. For example, if you need the layer of virtualization, you will use it. If not, the generic architecture will include it, but it is not obligatory to use it. It will depend on each domain, and this is we will do this generic architecture conforming to ISO standard, because they have the same idea to propose a generic architecture, and then we can adapt to each context and domain.
Yeah, exactly. Thank you. So for the interoperability, what do you think that we can use?
Notably for the interoperability layer, we have a lot of issues and a lot of challenges. Yeah. For these, there is the layer of middleware. We will detail it in sub-layers to include all the functionalities that must be included in our architecture. For example, sorting data, or for example, making an API in order to make the data homogeneous. So we will work in details in our next
Okay.
Each supplier into
Perfect.
their functionalities.
Okay,
Okay,
perfect. Thank you for your response.
Okay, thank you very much. We will pass for the next presentation. Olivier Debourg, Said Mahmoudi, and Hia Moussaoui. If you are here. Okay, okay, thank you. Thank you very much. Okay.
My name is Miriam Almilad, and I am presenting on behalf of my colleague Oliver de Bosch from the University of Mons, Belgium. As a
Okay,
part
okay,
of
d'accord.
our contribution to the 5th International Conference on Cloud Computing and Artificial Intelligence, Technologies and the Application of the year 2020, we bring to the table this year a variety of use cases to open up the general public to the learning of IoT and better understand the application as well as the interaction of this new technology in their daily life. This presentation will be as follows. First of all, we will define what does mean smart building in the introduction. Second, we will present the background of the study. Third, we will provide an overview about the different materials and softwares used in our use cases. Fourth, we will explain in depth the methodologies followed to build our cases. Finally, we will sum up the main finding in conclusion. Let's get started. As everyone is aware of, in this new era of technology, we are reaching a new age when it comes to building construction. No longer is enough for our homes and offices to provide shelter and keep us warm. Today, thanks to the evolution of technology, it is possible to not only deliver all the services that we need, but this can be done as efficient as possible by minimizing costs and reducing the environmental impact of the building over its life. So, what is a smart building? Is when that is using technology to share information about what is going on in the building between systems so as to optimize the building's performance. This information is then used to automate various processes such as security, fire safety, lighting, 24 hours per 7 days monitoring, HVAC, that stands for heating, ventilation, and air conditioning. The keystone of a smart building is to avoid the waste of energy. For instance, a light left on in an unoccupied room or a space heated when no people are around to enjoy the warmth. In fact, the main motivation behind the smart building is to avoid this kind of wasteful use of energy and resources, both to cut costs and to improve energy efficiency. Next, we are presenting the background of our study. In our previous works, we developed a practical approach allowing us to progressively learn by practicing. As you know, practice makes progress. The important concept of IoT applied to smart home, as we see in the screen, and also to smart city that we are published in they were published in international journals, as you see in the screen. Now we are shedding the light on the different materials and softwares used to build our use cases. Our demonstration hardware is composed of 3 main materials packages: smart home that contains a commercial sensor, do-it-yourself sensors, and smart building that contains an ESP32 affordable microcontrollers and MQTT server, and a smart city that contains an ESP32 microcontrollers equipped with LoRa. The first device is this little big eyes monster that we see in the screen. It is an HCSR04 ultrasonic distance to sensor. Now, as its name applies, this little device uses electronic sound in order to measure the distance between itself and the nearest solid object. The second
The sun is mute. We don't hear you, lady.
Okay. 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 I have some problem with the sound, please. I have some problem with the sound. Un problème de son, il y a un problème de son. Il est simplement...
Le problème, c'est dans l'enregistrement. Il n'y a pas le son dans l'enregistrement de la vidéo.
Ah, ok, d'accord, c'est bon. Ok, ok. Thank you.
Et je pense que les auteurs ne sont pas là pour commenter la vidéo. Si un auteur est là, il peut commenter la vidéo.
Donc, ok, ok.
Hello everybody. Today I will present you my paper entitled Formal Modeling and Validation of Microsmart Grid based on Ready Architecture. The outline of the presentation is as follows. I will start by a general introduction, then I will present our proposed Ready Architecture. After that, I present microsmart grids followed by a modeling of microsmart grid case study according to the Ready Architecture. We use this architecture for formal modeling and validation purposes. At the end, I give a general conclusion with most relevant perspectives. The traditional power grid has remained unchanged for a long time. The new context where we live requires an adaptation of the existing grid in order to be able to bypass a set of new challenges, namely the increase of energy consumption and population. This requires more and more energy production while conventional resources are limited and have a negative impact on the environment. This is why humanity is moving towards less polluting energies with what we call sustainable or renewable resources, such as solar, hydraulic, etc. The adoption of these renewable energies faces several challenges, namely the geographical distribution of the resources and of the power generation. On the other hand, renewable energies are said to be intermittent because their production depends on weather conditions. Taking into account this new configuration of the power grid, the concept of smart grids is introduced. These smart grids integrate a data network in parallel with the traditional electricity distribution network and offers tools for monitoring, analyzing, and controlling energy production and consumption in the power grid. Similarly to many IoT applications, smart grid should satisfy a set of requirements, mainly reliability, dynamism, and scalability, because the smart grid needs to be continuously extended, and adding or disconnecting an entity must not impact the operation of the network. The objective of this work is to ensure the balance. Otherwise, power companies to take advantage, then we can modify parameters for managing the power grid phase, an AMI in order to obtain an incremental and iterative design based on formal validation results. In the ready architecture, we consider that the global system is composed of several subsystems. Each subsystem is composed of several components, and there are three types of components. We have detection units, which are components responsible of detecting environmental changes. We have action units, which are components responsible of executing actions affecting the external environment. And at the end, we have the governance units, which receive the information from detection units and take adequate decision and send it to action units. We should notice that each subsystem is composed of at least one governance unit and several detection and action units, and that the governance units can communicate between each other. Now let's present the micro-smart grids. In fact, to set up smart grids, there are suitable technological solutions. We mainly find the advanced metering infrastructure, which is a solution made up of several modules aiming to help power companies to take advantage of new technologies for managing the power grid. An AMI system mainly consists of the following modules. We have the electronic devices equipped with consumators or smart sockets to control the consumption and transmit it to the smart meter. We have the smart meter, which is connected to all the customer's electronic devices.